Thank you, Guillermo. I guess that everyone can hear me also from behind. Okay. So, well, thank you for inviting me today to be here. And Guillermo asked me to talk about photonic integration platforms. And in fact, he suggested that I address these three topics. First of all, that I describe the photonic integrated circuit ecosystem. Second of all, that I address which are the different fabrication foundries for the photonic integrated circuits. And finally, he asked me to make a special section on our developments together with the National Center for Microelectronics in Barcelona on a silicon nitride platform. He asked me to do that for 1 hour and a half. I guess that I can do that more or less in that time or even less, so we can catch up with the schedule maybe. Okay, so the first part is photonic integrated circuit ecosystem. I guess that everyone here knows already what photonics is because you've been exposed to previous talks. So basically, all the science that deals with the generation, transmission, modulation, detection, etc. of light. And what is most important to me is to mention that this does not happen at a very particular wavelength, but the photonics cover a broad range of wavelengths. And the contents of the presentation are actually motivated in solving this problem. I think that those of you that have experience in a lab, are the micro switches on? Okay, now maybe I can stay here. So all of you that have been exposed to a lab, either it is photonics or not, you have been exposed to this kind of setups where you just do your, you assemble your system, you have your instrumentation. Typically for those that deal with photonics, I feel pretty uncomfortable with the microphone. So typically those of you that have been exposed to photonics, no, that's fine. Everyone can hear me, that's fine. So you've been exposed to this kind of setups with, 2 by 1 meter square setups. And if you deal with optics, free space optics, with all kinds of components that are somehow, yeah, they are nice, but they are bulky, but it is for sure that you cannot carry them on your backpack, right? And then photonic integration, which is something that is not actually in its concept very new. It already appeared in the Bell System Technical Journal by the 1960s of last century. Is some sort of technology that in summary tries to miniaturize all this in such a way that it can somehow isolate all the system from the environment. In those tables, if you step very hard at the side of the table, all these optics will vibrate and you are going to disturb the functioning of your system. So this photonic integrated thing is aimed at isolating from the environment. Oh. So it looks like we are being recorded, and someone in Valencia asked me, is this going to be recorded? I said no, but now that I know yes, then audio in the microphone is fine. So if I shout very, very much, please tell me, just don't shout, because I tend to shout a lot. So what I was trying to explain here is that the integrated optics concept stems from the need to isolating all the system from the environment. And then another consequence is if you can make that sufficiently small, then you can use mass production technologies, and then economics will result. Okay, so that is it. And today, and we will go through this along the presentation in several points. There are photonic integration companies. One example is ours. It is not the only one. We will later on see other examples. There are companies that actually take these systems, which, for instance, this one is from a Portuguese company. By the time I did this slide a long time ago already. And you can see they have this instrument with fiber optic components inside, which are spliced and assembled all together and put into a cage in such a way that they perform some optical function or optoelectronic function. And you can take this system concept and then the fabrication capabilities of others and turn it into a photonic chip, which is packaged and then small, and it will be small. It will be cost effective because it will be manufactured by mass production means. And then that means that you can scale up your production. It will ultimately result in power consumption savings. You only need to stabilize one component and not several here that are separated. And in some of the cases, not always, but in some of the cases, you can get increased performance. So this slide somehow contains or builds upon the past of the electronic integrated circuit, semiconductor electronic circuits industry, which started in the 1950s, and we're going to review this in this slide, where companies, so-called IDM, which stands for Integrated Device Manufacturers, they did everything in-house. That means that they manufactured the machines to do the processes. They developed their own manufacturing processes. They developed their own tools to design for these processes. They developed their own device ideas. They manufactured the device, they packaged the device, and they sold the device directly. So everything was done in-house. We have examples of that in photonics today. We will see some later on. But a long time, there were some parts of these activities that were disaggregated. For instance, one of the first was the manufacturing tools. So some people realized that the manufacturing tools that were used, for instance, by IBM, AT&T, is that a question? No? I mean, you can stop me at any time, I guess, right? Okay. So the manufacturing tools were similar for the different companies like AT&T, IBM, etc. And there were companies that started to manufacture these manufacturing tools separately and selling to the others. And then the tools that were used to design the circuits, the so-called electronic design automation tools, later on we will hear about photonic design automation, which is the equivalent for photonics. They were also similar for everyone, so actually some groups span out from the companies, from the large companies, and create small companies supplying software tools. And that also gave birth to fabless companies and foundries, because some companies realized that the manufacturing processes were very similar. They can be done in common for many other companies, as well as some companies realized when the foundries were available, it was no need anymore to have a foundry attached to myself. I could use the process from others, the tools from others, and then design my own concept without having everything in-house. Okay, so photonics is more or less here today, like in the 1980s of last century in electronics. That is what this graph tells us, or I want to tell. And then on the right-hand side, what you see is the comparison of IDMs, which are these like big companies that make all themselves in electronic ICs, and you also see the fabless companies, okay, those that resort to the capacities of others to build their own products. And you see the worldwide sales evolution from the 1999 to 2012. I think it's a very representative period because there was a couple of crises along that period. Okay, the telecom bubble burst over here, and then there were also the downturn due to the financial crisis in the close to 2010. And you can see the evolution of the worldwide sales, and you can see these downturns here. And then you can see the evolution of the sales for the fabless company, which is steadily growing. Of course, there is a small downturn here as well, but not as big in percentage than the worldwide sales. So that graph means that the fabless way of doing business seems to be a nice way of doing. And the question is, why is this not mirrored by other fields like photonics? And in fact, is what it has happened. It has been mirrored by other fields than photonics. So if we go into photonics, then we can see the evolution since, let's say, the concept paper in the late 60s of last century of integrated optics. And along the 80s and 90s, there were companies which were vertically integrated. They were IDMs in photonics. And they, their way of doing business was to select a very precise market and a very precise component or set of similar components that could be manufactured in the same technologies. They built the fabrication facilities, they owned the fabrication facilities. They developed the specialized, and the word is specialized here, the specialized manufacturing process to be able to do either laser, very good photodetector for a target market, very target market. And since also actives, but also passives like splitters, array waveguide gratings, variable optical attenuators, etc. And since they made a huge investment in the manufacturing facility and developing the process, they require a large return, or meaning that they require a large market or volume market. Okay. Then we had, that was the case, for instance, that for PLC, which is a silica on silicon technology, which is the most resembling thing to an optical fiber, but in a photonic chip. Then in the 2000s, we had the telecom bubble burst, and well, this way of doing business was no longer successful for everyone. Only a little have survived since then. And what we had in Europe was the recognition that maybe there was a way of doing fabless business as well in photonics, and there was an investment at the R&D and at the R&D level, and also pushed by public bodies like the European Commission, in such a way that a fabless ecosystem was created for photonics. And later on, we will describe that fabless ecosystem. And some companies emerged from these ecosystems, which I can say, in my opinion, they are quite successful. These two are two examples from the Netherlands. This one is here from Madrid, Mellumix, a close by company. But on the other hand, there are still vertically integrated companies that you may know or may have heard about them, like Infinera, Luxtera, and a few others. In any case, the market analysis and forecast show that there is a growing photonics market, overall photonics market, and I allow myself to mark here in which of the different segments of the photonics applications, photonic integrated circuits may be of use. Okay, and that there is an estimation that this market will grow to $55 billion in the sense of the UK or US concept. In 2020. Okay, is there any question up to this point? No, because next is trying to describe this part here about the how fabless is possible in photonics. And yes, please. Yes, Shio, yes, thank you. Yes, Mirvais is pointing that this company was actually, I mean, this company, Shio, was part of a big holding, I think, that Phoenix is also part of that holding, which was held by Pantera Group, and Pantera Group is a group of companies comprising Lyonix, Phoenix Software, Shio Photonics, the other one of the water that I don't know the name, several that are in the Enschede area in the Netherlands, close by to the University of Twente. And they've been doing like the fabless business model, but they are a group. Finally, they decided to integrate vertically in what they call now Lyonix International. Is that what you were actually pointing, right? Because now they have realized that maybe it's the time to go back to the vertical model. Yes, because, I mean, fabless is like, you know, well, let's do generic processes. I'll describe what a generic process is in short. And let's target like a very niche market, which are like very specialized and they require very low volumes, but still it pays off. But now the market is taking off, and that means that maybe there is opportunity for huge volumes for some applications. And in some cases, then getting back to the vertical model is interesting. Thank you for the remark. Any other question or remark? No, okay, so then let me describe how this was possible, or it is still possible today. And that is thanks to something that already happened in electronics, and that happened in photonics, or started to happen in photonics by 2007, I would say. to explain that, I like to use this toy analogy. Maybe some of you have already seen this presentation, or sometimes in the past. And I use it because I think it pictures very well the difference between a dedicated manufacturing process and a generic manufacturing process. Before I said vertical integrated, specialized process, dedicated process. That means the same thing, and that is a process that allows you to fabricate a single specific thing. For instance, a process that allows you to fabricate Buzz Lightyear maybe does not allow you to fabricate his friend body, okay? Only fabricating Buzz Lightyear. But on the other hand, you have a generic process, which is, for instance, in the toy analogy, is Lego, where you can fabricate multiple diverse things out of the same little pieces, okay? That is generic versus dedicated. In electronics, you have the CMOS process, where you have fundamental blocks like the resistor, the capacitor, the inductor, and with the combination of those, you can make circuits that do many different things. In photonics, you have like the waveguides, the phase shifter, the optical amplifier, and the polarization handling blocks. These are the fundamental functions. You can combine them in such a way that you create what we call a building block. For instance, this piece here is like an MMI coupler, which is a combination of waveguides that results into a coupler. And then if you combine several building blocks, you get at a higher abstraction level, you get a composite building block. For instance, I mark here this one. This is a tunable laser composed of 2 DVR mirrors, semiconductor optical amplifier, and phase shifting section. And when you combine building blocks and composite building blocks and fundamental functions all together, you get a photonic integrated circuit. In this case, that was an integrated microwave photonics filters we recently published. So as I said, one of the conditions that allowed to do fabless in photonic integration was the availability of generic integration technologies. The second one is again a mirror of a microelectronics way of doing things, which started in the 1980s in the US universities. They had their courses on semiconductor IC design, but fabrication was very expensive for the students of one course to take a full wafer of design. So they actually decided to team up with other universities around the United States, take a small part each of the cell, so to design only a small part of the cell each university, and then submit the whole mask, the whole wafer design to a fabrication run and share the costs, okay? So those are called shared access runs, shuttle runs, and most common use term in photonics at least is multi-project wafer, okay? So you share the area of the wafer and you aggregate the design of different users in such a way that you only pay for the area that you are using, okay? So these two things, generic technologies and multi-project wafer, have made us, a lot of people in photonics, to increasingly use these technologies. So I think that I come to the most boring part, if this was not boring, to the most boring part of my talk, one in which I review supply chain. And that there are many different supply chains overviews. I think I took this one because I think it's quite representative. It is from a Silicon Photonics market report. I think there is an update in 2016, not quite sure. 2014 is the last one I have, a list, and it divides the supply chain from research up to end users. And then research, MPW, design houses, fabless companies, foundries, device and module manufacturers, system integrators, and finally end users. An updated document that I had access yesterday is this one from EPIC in 2015. There is maybe a little difference between this supply chain overview and theirs, but the companies that are here are already there, and you can see their description if you wish. I will skip this not very slowly because I understand that maybe this is not very technical and maybe it's a little bit boring. So in research and development, we find both the availability of sharing the cost, as we said, and the availability of generic processes. This I have already mentioned in such a way let me insist that you, as a user, use only a small part of the area of the wafer, so you share the cost, and your design uses the same building blocks and the same technology than this design, but the target market and application can be very different. One can be the telecom, and the other one can be the sensor market, instrumentation market, whatever. It is not complete, but I think it gives a picture of the three main generic technologies available today in the market, which are silicon on insulator, indium phosphide, and silicon nitride, or even in some cases PLC. And these are the different fabs that are available in each of them. Some of them have already quit the generic technology market because they have enough product demand now to fulfill their capacity. That is the case of Oclaro. And you can get access to them either directly or through broker organizations or umbrella organizations like Europractice, which in fact comes is the equivalent to the MOSIS United States initiative, but in Europe for electronics. But now they incorporate some of these photonic processes from IMEC, CLETI. I think that they also incorporate some from IHP. There is, on the other hand, JEPIX that comes out from the Technical University of Eindhoven, and it fundamentally is an umbrella organization for indium phosphide and some of the silicon nitride. EPIX Fab is the same for some of the silicon nitride as well, and for the silicon on insulator. We will see them later on. Here there are some figures. These are from 2015. They're a little bit outdated, I know, but they give you an idea what you can find in the market. You can find different indium phosphide technologies, different silicon on insulator technologies, and some silicon nitride technologies. What I want to convey in this graph is that, for instance, if you stop yourself comparing some of the performances of some of the building blocks, for instance, these indium phosphide detectors or these indium phosphide modulators, well, you see that despite they are all indium phosphide, the performance or the predicted performance is different for the different platforms. That is an open issue in the field because that means that you can not easily, or sometimes it's impossible, transfer one of your designs from one indium phosphide platform to other, or from one silicon on insulator platform to other. So at some point there is some group of people that we are convinced that there should be some technical convergence between the platforms in such a way that if each of them provide 2-3 MPW runs per year, you would multiply your access opportunities if all the technologies were more or less similar. Okay, and then for instance, this slide, it is not updated either, but it is quite up to date. If you remove, for instance, Oclaro, should be quite up to date. There are more foundries and other technology brokers as well around. But for the different technologies, this gives you a picture of the different building blocks that you can find for guiding light, for coupling light, for connecting your chips with optical input and output fibers to modulate the light, to filter the light, and actives like the detectors or the amplifiers and the lasers. Okay, so this picture is today more complete because there must be some greens here for smart photonics, etc. But at the very end, it can guide you at least at the first stage to decide where your chip can get manufactured. For instance, if you have a photonic system concept in mind for your research or for developing in your company, and you want to, at the first sight, see which are the possibilities that you have to get it integrated onto a chip, then you can look at this table and search for the greens, for the building blocks that you are using or for the functions that you intend to use. My system has a laser, a coupler, and a detector. Well, then in this case, you can look at this area, you can look at this area and see where you can get it integrated. Monolithically integrated. That means using only a single of these technologies. So if we step one link forward through the supply chain, we have photonic integration companies or design houses, that depends on how you call them, One of them is, as Guillermo said, one that we started in 2011 and is still running and growing, which is VLC Photonics. But there are others like Bright Photonics in the Netherlands, Ekfed Photonics, which started as a design house, but now is a product-oriented company, supplying transceivers for short, medium reach, if I am correct. And there are others like Lucida Photonics, which is maybe software vendor, but it can supply design services as well. If we step one link forward in the supply chain, we mentioned the existence of fabless company, for instance, Luxtera, that uses CMOS foundries elsewhere. It's a company which is been around already since 2001. Former spin-out from the Belgium University, Calliope, that was acquired by Huawei for optical transceivers. Scorpius Technology, which is a fabless semiconductor company that provides transceivers as well based on a proprietary silicon photonics process. Aurion in the US, a spin-off from UCSB, etc. There are many companies, many fabless companies. When you aim at doing a large volume manufacturing, at least in silicon or CMOS friendly environment, you find STMicro, Freescale Semiconductor, and TSMC, which actually are incorporating silicon photonic process in their portfolios. And device and module vendors is the next step in the chain, at least in the Yole market report. There is Avago Technology, which is a very old established Singapore-based company. Colorchip, which was recently acquired by Mellanox, if I'm right. And then there is Infinera, which is a vertically integrated company supplying indium phosphide-based solutions, not only the components, but also the networking equipment. So they are totally vertically integrated, and Finisar as well. There is another part of the ecosystem which I also like to describe, which is the organizations that somehow support all this ecosystem and perform activities to promote the ecosystem. For instance, there is the European Photonics Industry Consortium. It does not deal only with photonic integrated circuits, of course. It deals with photonics at large, and they do advocacy, lobbying, market and technology reports, presentation and publications. And most important maybe for all of us, apart from the market and technology reports, which tend to be very useful, networking and events which bring us all together, and there are the very right place to interact with people in photonics in general, and in different fields of photonics that can have complementarity and create synergies. That is EPIC, which is a private organization, I would say. And then there is Photonics 21, which is stems more or less closely to the European Commission and somehow tries to establish guidelines for research. So actually it's also governed by companies, but tries to establish, as I said, guidelines for research. And these guidelines for research are somehow later on fed to the public programs like the European Commission Horizon 2020. And in the United States and Japan, you can find similar organizations. I'm not going to stop there. Even worldwide, you can have organizations that somehow combine or combine all these regional organizations. Okay, so you've seen that the PIC ecosystem is somehow, the picture is wide, and there are very different actors. So if you are interested in getting your solutions, your photonic systems into photonic integrated circuits, then to enter the ecosystem is at the very beginning you can be lost. And there are initiatives like this European Coordination and Support Action, of which the Technical University of Valencia is member, which is PIC4TB, where we try to guide and support interested users in getting inside the photonic integrated ecosystem. So actually this is one of the first doors to you if you are interested in making use of photonic integrated circuits. If you need that, you can contact me or contact directly the consortium through our website. Okay, that was like the first part of the talk. Second part is more related to technological aspects. So for those of you that have technical interest in photonic integrated circuits, maybe this is the right part, this and the next. Well, this picture tries to capture in a single shot what we have in photonic integrated circuits and what does it cover in terms of applications. Applications are usually very tightly mated to the wavelength of light. Okay, so whether this is an application of biophotonics or telecom, that usually happens at a particular wavelength or a particular wavelength range. Okay, for instance, tele and datacom have traditionally happened in the near infrared. That means the wavelength range for which the optical fiber, the silicon optical fiber, is transparent, or at least has low loss, very low loss. Then biophotonics usually happens around the visible wavelength range because visible light is harmless for biological tissue and biological samples. Okay, so well, in fact, we are exposed to visible light, and unless we stay in the sun for long, nothing wrong happens to us, right? So to test or to analyze with light, biological samples, usually the visible wavelength range is preferred. And sensing, I think that sensing can extend even down to the visible, but sensing, that depends on what you are willing to analyze or to sense. That depends on the material substance or analyte, that is called an analyte usually in the field of sensing, that you are targeting, because the different molecules will have characteristic resonances at a given wavelength, and it does not need to happen in the near infrared or visible. In fact, the characteristic ones happen close to the end of the near infrared, but you will have second order, third order resonances when you go down to the mid infrared or to the near infrared. So to uniquely determine what type of molecule you are analyzing, if you do that in photonic technologies, you usually need, or you are maybe required to use wavelengths in the mid infrared. Okay, so we have these wavelength ranges here: visible, near infrared, mid infrared. Now that is photonics at large. If we try to correlate that to what we have in photonic integrated circuits, then we come to the bottom part of the graph. Okay, for the different technologies that I just introduced before, and that I'm going to describe a little bit more in detail in the next slides, we have 3-5 semiconductors, we have the silicon on insulator, we have silicon nitride. I have not talked about germanium on silicon, but I'll do it now. These ones cover ranges, for instance, 3-5 semiconductors, typically the near infrared, up to 2 microns, a little bit above, I would say, from 0.9, 0.8 microns. Silicon nitride on silicon oxide technology covers from the visible up to, well, if we are quite loose, up to close to 4 microns wavelength, okay, where the silicon dioxide starts absorbing. And then silicon on insulator is silicon on silica. Then has a transparency range of the silicon. Actually, the limitation here comes from the silicon that is transparent above 1 micron, if my memory serves well. Then if you want to go up in the wavelength range, then you need to use materials that are transparent in that wavelength range. For instance, you need to avoid silicon oxide that absorbs from 4 microns above, and then you need to resort to combinations like germanium on silicon. But that is not the only solution. At the very end, you have these technologies, and you have these foundries here, or these suppliers here, that the graph only shows suppliers that provide multi-project wafer runs and generic technologies. Okay, so that means that you can find many other suppliers or manufacturing partners that supply dedicated runs for the different technologies. But these one at least are the so-called open access, the ones that you can knock at the door with one design, and you can get it manufactured cost effectively through an MPW run. Okay, So this picture here tries to capture in, let's say, 3 large groups the different ingredients or parts of the ecosystem: the actors, the software suppliers, and the brokers. Okay, so let me start through the actors. Actors, we already described several. Design houses we already did. Fabrication partners, we're gonna do it in short. And we're gonna skip these ones, but they are also very important, which are packaging and assembly companies. Packaging and assembly deals with handling your chip and housing it in such a way that you can make use of it. And as I say, they actually condition, in most of the cases, how you design and for which platform you design. Then here we have computer-aided design or photonic design kit supplier companies like Phoenix Software that we're going to get a talk later on. Purely photonics one are Phoenix Software, Photon Design, which are somehow very well established in the field. Most recently, Lucida Photonics. And BPI Photonics has been doing for systems, but somehow are incorporating photonic integrated circuits capabilities to their design suite. And the other ones, Mentor, Cadence, Synopsys, well, I skipped numerical, sorry, it's some sort in between, should we say, the capabilities of VPI and others like Photon Design and Phoenix Software. And then Synopsys, Cadence, and Mentor, if I am right, they are suppliers of electronic IC design software and somehow are incorporating photonic capabilities or photonic design and layout capabilities to their software as well. Then we have already mentioned these organizations before, broker organizations that somehow aggregate the designs of different users and then handle the runs at the different fabs. Okay. So, for instance, if we break this into the JEPICS and the Europractice ecosystem, so the indium phosphide and the silicon ecosystem, if we are allowed to describe it like that, then we find in the value chain part of software tools, sorry, we find these companies: Phoenix Software, Photon Design, Filarete as PIC Design is included in Phoenix Software, if I'm right. Yeah. And then design houses we already mentioned, BLC and Bright, aggregator in this case JEPICS, and fabs in the case of indium phosphide or JEPICS, we find Fraunhofer, Smart Photonics, No Longer, or Claro. Okay, Lionix is silicon nitride, but somehow is a member of JEPICS and also of EPICS Fab as well. And then as a packaging houses, we find Linkran Technobis for indium phosphide. Let's describe some of the technologies of indium phosphide. For instance, this platform at the Heinrich Hertz Institute in Berlin. This is a platform that's been around for many years and created through research. In fact, it is the origin of one very successful company, which was US2T. US2T was a company doing receivers, basically, detectors, and later on coherent receivers. And that was acquired by Finisar like 2-3 years ago, if I'm correct. But that platform was already extended not only to incorporate the detector and the guiding waveguides, but also to include active material. Okay, so this active material is included to provide amplification, but it's also combined with some lithographic techniques to make gratings, so you can make lasers. In fact, you can make DFB lasers, and you can make also tunable DVR lasers. So this is a sort of monolithic platform. You can have everything in a single platform. You can have the passives, the actives, and the detectors. If I'm right, either they roll it out recently or they are planning to roll it, because the only thing that is missing is a phase modulator, a fast phase modulator, based on the electro-optic effect. They do provide modulation based on thermal optics, which is slow, and on carrier injection, which is somehow maybe not the very best convenient for some of the applications of indium phosphide chips. It works on the C-band wavelength range that is 1550 nanometers and 30 nanometers around that wavelength, which is the third transmission window of telecom optical fiber or standard fiber. Most of the platforms do also provide, and I think that the knowledge of this is important, knowing this is important, different waveguides. That means that you can either make your circuit with this waveguide, or this waveguide in the case of this platform, and the properties of each waveguide are different. So that, depending on what you want to do inside your circuit, you will use one or another. For instance, this one, which they call E200, is a waveguide which is shallowly etched. Okay? If you compare it to this one, where you see that the material is etched or deleted, if you wish to use that informal way of saying it, it is deleted down to nearly the substrate. Then the difference between this and this is the optical confinement. Optical confinement. And optical confinement means how broad or how large is your optical mode with regards to the waveguide dimensions and index. And in this case, you will have a confinement which is, if we can say that broadly speaking, smaller than in this case. Here, light is more confined than here. And that means that when you usually make your circuits, you don't only make a straight waveguides, you also make bends. And when you make bends, if you make them very narrow, if you bend them very narrow, then the light tends to escape the bend. It is the same thing that when you go with your car and there is a sharp bend in the road and you go very fast, then if the turning is very, very sharp, then you and your car will get off the road, right? So it's the same thing for light. If you make, for instance, a very narrow bend here, and your light is not very well confined, light will escape and will result into losses. That's dangerous. You don't quite agree? Yeah, of course you don't. Yeah, of course you should not be doing that with the car. But I found that from all the analogies I tried to picture out from my master students, I think that was the one that worked best. I don't know if it worked here, but for my students it worked. And however, if you use this waveguide to make narrow bends, that is fine because you are very well confined inside the road, which is the waveguide. But of course, everything in engineering comes with a trade-off. That means you can make a small circuits with this one, and with this one you can make them large. So question is, why would I use this waveguide at all? Because we didn't say it explicitly, but somehow I mentioned it. The fabrication cost is per area. So actually, if you can make it very tiny, why would you use this waveguide that will result in a very large circuit? Well, trade-off is optical loss. Since you etch this waveguide down to the substrate, the roughness here felt by the light is larger than the one that the light feels here, where you only etch a little portion. So this one usually has larger propagation loss than this. So circuits for the routes in your circuit where you need to go from one side to the other, let's say it that way informally, you usually employ this type of waveguide, which is less lossy than the other one. And when you need to make very compact part of your circuit, then you use this type. And you have elements to transition from this waveguide to the other. This one is something like in between these two. Okay, is that more or less clear? Okay, fantastic. Then these are examples of circuits done by several of us in the platform. This is sort of excellent receiver by Bright Photonics with many AWG, cascaded AWGs, primary AWG. I cannot see the primary one. I think it's somewhere over here. And then like secondary AWGs and close to 100 detectors, if I am correct. Then we did this receiver for microwave photonic links. And there are several others like the terahertz source and opto RF converters. As you can see, digital photonics is not the only applications of photonic integration, but there are also other applications like analog communications like microwave photonics or terahertz. Yes, please. Okay, your question is if all of them are not the same scale. No. Yes, they are a different scale. I would say that this, I only know this one because it's the one that we did it. It is like 6 by 6 millimeters square. This is maybe a little bit larger. I don't know, but this need to be smaller. Yes. Yeah. Yeah. So, so your question is about the different die size or chip size, even inside the same manufacturing platform. Oh yeah. Yeah. Yes, what Guillermo is saying is really more and more details about the same thing. I mean, there are different foundries, and they even the same thing they do it the other way around. He's talking about how the waveguides reach the facet. Sometimes you make them at an angle to minimize reflections, and he says that some foundries make them this way and the others that way, and that's a nightmare for packaging. Yes, yes. Despite there have been some efforts and projects to do packaging templates, there are still some these basic disagreements around the field that you need to know. And then it's a nightmare to transition your designs from one fab to the other, yeah? Yeah, but hopefully, I mean, those things should be solved along the... Yeah, semi-insulating platform, yeah. Yeah. It's M+. Yeah. As the angle waveguides. Yeah. Yeah. That is true. That is true. But I mean, we all know that these platforms somehow were developed in parallel and not very synchronized, and that they got together like at a middle age, not at the early age of them. And then now somehow they should converge. I don't know how to solve that, but the guys running the platform should do. At least from a user perspective, it should be easier. Okay. Any other question or remark? Okay. Well, Smart Photonics was a spin out of the Technical University of Eindhoven, and they took over their process with as well with amplifiers, two types of waveguides, shallowly edged, deeply edged, and electro-optic modulators in this case. And as far as I know, they incorporate already detectors and DVR-based lasers. Some chips, as I said, not only telecom ones, but this is a wavelength meter, I think, widely tunable laser, and optical gas sensing mode lock laser. Claro, I'm going to skip it, but yeah, we have done some work also there. But basically, it comes from Oclaro, which is a company devoted to make transceivers, and owing to that, you can do all sort of telecom-like chips, but not only for telecom, I think, but also you have here an example of a pulse compressor for bioimaging. Then we have the other supplier, Technology Foundry, that is part of JEPIX as well, which is Lyonics International now. This is the same logo, but in red. And then they do silicon nitride waveguides. We will talk about silicon nitride in some extent later on. But fundamentally, this is a passive platform, and it may seem that a passive platform has no interest at all, but it is very low loss platform. So for those applications where you need a long recirculation of light, a long distance for light to circulate, these platforms are really important. Like, for instance, when you try to process microwave signals in the photonic domain, where you can make delays among them, and then you need to make them run through long optical waveguides, then the optical loss is very, very important. And the good thing of these platforms based on silicon nitride, not only the one of Lyonix, this is inherent to all the silicon nitride surrounded by silicon oxide platforms, is the transparency range. You can use them from the visible up to above 2 microns. So if we go to Europractice, then and the Europractice, we have more or less the same, or should we say the same software suppliers, same design houses, different design aggregators. MOS is serviced in United States. Now AIM Photonics as well, it's not here in the picture. EPIC4TB, I show some EPIC4TB slides in short. And then Canadian, I don't remember the name, that's in Canada, CMC. And I think it's Canadian Manufacturing Center or something like that. And sorry? Microelectronics Center, thank you, Canadian Microelectronics Center. And then fabs, list in Europe, you have these 3, there are some more, but these are the ones that fall under Europractice, and packaging service by this institute, Tyndall. So let me talk a little bit about EPIC4TB, of which our group is a member. EPIC4TB is an alliance of European organizations to promote silicon photonic science, technology, and applications. So actually, as I said, the aim of EPIC4TB is to promote, to represent the silicon photonics community, and to train industry and academia in the use of the technologies, as well as to supply roadmaps on the evolution of the technology. All started with some projects we participated starting in 2006, where the generic technologies and the multi-project wafer runs were defined not only for silicon photonics, but also for indium phosphide. So EPIC4TB is the spin out of that activity, those activities for silicon, and JEPIX for indium phosphide. Some projects follow up, some technologies were handed over to Europractice, so similar to the electronics, they can be accessed to through Europractice for photonics. And today is an open alliance, so everyone willing to be member is mostly welcome. And it is formed about companies and institutions. So we have as coordinator University of Ghent, the group by Professor Roelbach in Belgium. And then these different fabs, I will show a picture later on relating which type of activity each one does, from IMEC, STMicro, LETI, ISP, VTT in Finland, Lyonix International, Ligentech Switzerland, AMO Germany, and CNM here in Spain. And then there are software suppliers providing design tools for the technologies in the EPIC4TB portfolio, design houses, VLC and Bright. And then technology brokers, the one that somehow collect the designs and provide you access, like Europractice, and CMP, which is a private company supplying access to the LETI technology. Okay, there are companies supplying epi wafer services like Brolis, packaging services like Tyndall, and then consortium or industrial consortium representation like EPIC. And of course, there are a lot of groups from the academic research, our group in the Technical University of Valencia, Aarhus, Germany, Denmark, everywhere. So this is EPIC4TB, and as in the training activities, training program for the coming years, there is a summer school done each year. There are design courses, and of course there are on-site trainings that can be tailored for specific needs, typically for industrial participants, but as well for academics if they require. As I said, I was going to provide a picture of the different manufacturers and what type of activity they do. For instance, the founders by IMEC, LETI, and IHP have like frozen technology that is accessed through Europractice or CMP. Industrial manufacturing in large volumes can be done by ST Micro. If you go to MPW, multi-project wafer and low volume fabrication of silicon insulator, you still can go to IMEC, LETI, ISP, but you can also go to VTT in Finland. You can use Cornerstone program in the UK at the University of Southampton, and you can use AMO in Germany, in Aachen. And then for silicon nitride, IMEC is establishing a new process. Lyonics has longest tradition in MPW processes in the field. And then Ligentech in Switzerland is a spin-out of EPFL, which is also providing a very interesting process for nonlinear applications. CNM in Barcelona, I'll describe it in the third part of my presentation, and AMO in Germany as well. So in one slide, which are the characteristics of the process provided by everyone, IMEC provides a SOI process for the O and C band, that is 1310 nanometers and 1550 nanometers, with 50 gigahertz bandwidth active devices, the modulators and the detectors. LETI provides two versions of the platforms, like passive plus heaters, and the silicon photonics are 1310 nanometers with a thickness of 1310 nanometers. No, 310 nanometers, sorry. And the EMIT is compatible for 3.5 laser integration, hybrid integration. And then another interesting platform is the one by ISP in Germany, which actually is the single one providing monolithic integration of big MOS electronic with photonic building blocks, like the waveguides, modulators, and detectors. Then on the other hand, should we say more low-scale foundries in silicon, there is Southampton, there is VTT, and there is AMO. In terms of the technology, all of them are similar except VTT. VTT provides a technology of thick silicon, that is waveguides in which the guiding film, it is not in the order of hundreds of nanometer heights, but it is 3 micron heights, and the waveguides are like 3 microns width as well. Whereas all the others are strongly polarization dependent. That means that you need to control very well the polarization that you inject in your chip, because actually it's going to somehow guide or propagate or treat polarization TETM in a different way. Then this one can be polarization independent. So should we say it is more fiber friendly, because you can use regular fiber phase to this kind of chips, and your chip will be polarization independent. Then for silicon nitride technologies, as I said, we have Lyonics since a long time ago with different type of technologies, not only stripe waveguide, but also double stripe. And then you have a triplex waveguide, and this one is another double stripe with different, this one is with different height in the different stripes. So each one has different properties, and that one is one with a thick silicon nitride. This technology from Ligentech is very similar to this one, and those ones are aimed at nonlinear applications in the long near infrared. I will mention something about it later on. And the platform that we have co-developed with CNM in Barcelona, it's a 300 nanometer height platform for visible telecom and mid-infrared applications. And AMO as well has LPCVD based platform as CNM, but as far as I know, they are not providing MPW services. So all the others are providing MPW services. So shared access, cost-effective access, dedicated manufacturing at AMO. Okay, so that brings me to the last part of the talk. Are you still alive? Okay. Okay, so let me describe a little bit the different, how we approach or who did this platform, and which are the technical features. So first of all, this platform is a combination of efforts from VLC Photonics, our spin-off company, and the Institute of Microelectronics in Barcelona, from the National Center of Microelectronics, the Spanish Research Council. And our company, VLC Photonics, is a photonic integration company that takes a system concept and turns it into a chip, supplying all these type of activities. system engineering, optical architecture, chip design, performance simulation, mass layout, and DRC. Not manufacturing, it is a fabless company, chip testing, and not packaging that is done by others as well. Despite we are incorporating instrumentation in the company to mount the chips up to some extent that you can use them directly in your photonic labs. We work as well with foundries, and we help them market their technologies. We have done that with several of these. Actually, BLC Photonics designed this process, made the design kit, and runs the MPW wafer, but also Ligand Tech as well. So BLC, if you have a foundry and you want to make it available to others to use your processes, you can contact our company. I'm going to skip this one, it's pretty commercial. And then these are examples of chips that we have done in many technologies. So sometimes I go somewhere and the indium phosphide guys tell me, yeah, BLC Photonics, you do mostly silicon. No. And then you go to the silicon photonics guys and tell you, and do the indium phosphide guys? No, silicon photonics guys, and they tell you, BLC Photonics, you do mostly indium phosphide. No. So we have done all chips in all the generic technologies and in other dedicated technologies. So we have done silicon nitride widely right now with Ligand Tech and CNM. We have done silicon on insulator elsewhere in IME Singapore, in Leti France, in IMEC. We have done indium phosphide in SMART, in Oclaro, in HHI, in many places. That means that we have a library of components, not only the components that the foundries supply, but we have also developed our own components where those were missing or did not have the functionality or the specifications that we required. Let me also tell that most of the work that we do in R&D is collaboratively. So we've done a lot of R&D cooperations elsewhere. I'm not disclosing names, but the different technologies. Well, some of them, for instance, it's already in the public. This quantum random number generator is currently a spin-out of the Institute of Photonic Sciences in Barcelona. Okay. And then CNM, it's a public institution. They have a CMOS line and clean rooms. Most of the funding comes from the EU and industrial contracts, some part of the national research funds. And they have many different processes, but they are, at least in the biophotonics field, they are known to have a silicon nitride-based process. And we approach them to make a more telecom-friendly process based on silicon nitride, and that is what I'm going to present here. We develop a fabrication process in which there are 3 waveguide cross sections with a film height of 300, shallowly etched half the film height, deeply etched down to the silicon oxide, and then one which is 150 nanometer height. On top of that, we added right now only thermo-optic tuners. That means that you can change the refractive index of your waveguides by the thermal effect. And something which is somehow unique until recently is that you can selectively etch away the cladding of your waveguides, so you expose your guiding layer to the ambience. That means that the light can interact with what is outside the chip. So you can make sensors. We have made waveguides, couplers, MZIs, SAGNAC interferometers, array guide gratings, HL gratings, ring resonators, everything. And it is a foundry that provides access through a shared access model, MPW. And we have done already three runs, and previous, let's say, informal run and then formal runs. And then the third run training course is in January in Valencia, co-located with an event that we did last year, the Photonic Integration Week, where we bring experts from the field and you can get in touch with experts from the field and then followed by a training course. And then the mass deadline is in February. Usually the chips are delivered 2 months after. And then you have different cell sizes. This one, which is 5.5 by 11 millimeters square, and this one, which is actually half the size. Okay, but silicon nitride. Why silicon nitride? Silicon nitride is not a very new material. In fact, it is a material that is very well known in electronic IC manufacturing. In most of the cases, not because it does nothing special itself, but it helps you to build your electronic IC. So it's like sort of helper material. If I'm allowed to say that now, there is maybe no electronic IC industry expert in the room. Early in the 90s, the CNM started reporting the use of these films. Of course, the first demonstrations in the literature are from the 1970s of guiding red light through a silicon nitride film. But doing it for some successful application has been done by CNM with some cooperators at the Catalan Institute of Nanoscience and Nanotechnology. And they do biophotonic sensors in the visible. Okay, that is maybe, that should be another talk completely. But in any case, they did that technology there, they spin out some companies and they sold the companies. So I can say that they are very successful. In any case, that was the use for invisible wavelength range and for biophotonics. But then a few years later, some other groups started to pay attention to that material, but for telecom applications in the near infrared, okay? Then, following that interest, some other groups and companies develop very low loss waveguides. Those are done by Lyonics mainly. And those waveguides, as I said, are the ones to make long delays in the photonic domain. In 2013, there is again a new interest in visible light application by different groups, and now there is a pilot line running, which is PIC4TB, of which our spin-off company is a member. But then you see visible near infrared, then visible and long near infrared. In this case, long near infrared because of the use of high confinement waveguides for nonlinear applications, such as supercontinuum generation and frequency comp generation. So this, as I said, is the platform. Now I'm showing here the cross-section, the shallow edge waveguide, the deeply edge waveguide, and the mini-deep, which is actually the same aspect than this one, but half the height. And the additional structures that I already mentioned, the thermo-optic heaters, which is a piece of metal that you put on top of the waveguide. You make some current flow through the piece of metal, and then you hit the metal. Heat is conducted through down to the silicon nitride. You change the refractive index, you change the phase of the light. And then selective area trenching, that means that you can open the cladding, remove this cladding on top of the area that you wish. In this case, exposing the silicon nitride to whatever is outside. This is what actually you can see here. Well, I can tell because I know the chip, but this square here is an area where there is no silicon oxide, where it was removed. Okay, so let me just enter a little bit more in technical details and explain how we tested the performance of the platform. I think that what I say here is not exclusive for silicon nitride. So actually, if you are willing to do a chip and for your application, some of these features is important, you can use these test structures in your chips and use proper measurement to get the figures of merit that you are interested in. For instance, propagation laws, you can get them either directly through the measurement of spiral waveguides of different lengths. You can tell from the picture different length, and or indirectly from Mach inverse, as I will describe later on. But not only the amplitude effect of the waveguides in your light, but also what happens to the phase, group index, dispersion by refringence, and for that we did ring resonators. Then thermo-optic phase shifter with Mach inverse. You can see them here, unbalanced Mach inverse, and this is a thermal heater on top of each arm. And then for optical I/O coupling, regular and inverted tapers. You cannot tell from the picture, but the waveguides here have different tapers here than here. Yes, there is one remark. Yes. You can do grating couplers, but because of different reasons, the efficiency is not to tirar cohetes, how we would say in Spanish. That means not very satisfactory, but because of two issues. One of them is for the efficiency to be optimum, you always need to select substrate height according to your wavelength. That somehow breaks the broadband nature of this platform. So I'm not advocating for them. The CTO of VLC, which is David, wants to do grating couplers. I don't want to do grating couplers. So we have grating couplers. They use them. I don't use them in my chips. But yeah, and the other one is the litho resolution, which we are limited because we are using an I-line stepper. So we actually not using the main diffraction order. We're using second, third diffraction order. And that's why we have less resolution. But as I will tell you later, we're going to solve that, at least that. Yeah. Thank you. Yes. You're going to see it in the next slides. 2 slides more. Okay. No, still have. You said 1 hour and a half, and I'm going to make it. I thought I was going to be faster, but yes, I'm finishing. I'm finishing. I have to mean. Yes, I should not have said that. Sorry. Okay, I'm going to be fast. I'm going to be fast here. Okay. Okay. Then before going into details, let me tell you that we developed in our lab an optical frequency domain reflectometry setup. This is nothing new in the literature. You can find how to do it, but it takes us some time to make it work properly. So it makes use of a tunable laser and some detectors with a digital acquisition system, and you embed your chip in a Mach-Zehnder interferometer, and then you use another Mach-Zehnder interferometer as reference to correct the imperfection of the tunable laser scanning. So actually you use the interferogram of this Mach-Zehnder to sample the interferogram of the Mach-Zehnder where your device under test is embedded. Okay? In that way you can retrieve the amplitude and the phase of your device, everything. So you get the field transfer function. So for instance, with the spirals, what we did was typical measurement like the OTDR in optical fibers. You can see the input event to the chip, the output event to the chip, and decreasing power that you can feed a line and get the propagation loss. If you read that paper, you can do that indirectly as well with a Mach-Zehnder that you need to design properly. If you pay close attention to this Mach-Zehnder, you will realize that the length difference between the upper arm and the lower arm is only in the straight sections. Everything else is the same. So the rejection of the Mach-Zehnder, which is due to the incremental length between the upper and lower arm, is only due to the straight sections. From them, you can tell the propagation loss, unless estimated with equations. This is a direct measurement. This is indirect measurement. Then for the dispersion, we use the ring resonator. What we did with this OFDR system is we actually get the output pulses. We get the output pulses for TE and TM of each recirculation. So it's an interferometric setup. So we get the precise position and time of the different pulses. If you put together pulses that are consecutive in time, at the same polarization, you can see the broadening. So this is the first pulse, the second, the third, and the fourth. You can see the broadening. If you make the Fourier transform, you get the dispersion. If you relate consecutive pulses, you get the dispersion of your waveguide, which is -4 picosecond nanometer per meter. Yes, that's normal dispersion. That's normal dispersion. But we have ways of tailoring it. If you're interested with anomalous, you can tell us, okay? We can engineer the cross-section. And I'm not going to stop with the heaters. The issue with the heaters was finding the right metallization so the heaters were efficient and were durable. And we're still there. We tried gold and chromium, and then we are going to gold, titanium, nickel, and now we are doing aluminum as well. So there are different types of heaters, okay? That is in the design manual. Another issue of importance is the coupling loss when you go with a lens fiber to the facet. And we use regular tapers, and we had 3.5 dB per fiber pond, but we did this inverted taper in which we taper it laterally, but we also use the cross-section with a mini dip height. So we actually expanded the mode in the horizontal and in the vertical dimension, and we got a 2 dB improvement per fiber point. So we got 1.5 dB per fiber point of insertion loss if you use the inverted taper. And then last part of the presentation, which are the plans that we have to make this platform of wider use. There is a growing interest in the mid-infrared because of the sensing applications. And the issue with the CMOS compatible platforms is that silicon oxide is used, and silicon oxide starts absorbing at 4 microns, I already said that, but the silicon nitride is transparent from 400 nanometer up to 7,000 nanometer. I skip this one. These are the platforms that are available today, and the guiding is restricted in this wavelength range. The lithography resolution is limited, so you cannot do fancy things if you wish with high resolution, like the grating couplers that Guillermo was asking about. Thermal tuners are present, but they have power consumption, except for Lyonix, that there is some piezo-based tuner, but it is quite large. And there are no sources and detectors. So what we want to do in the coming 3 years is, first of all, to extend the guiding up to 7 microns, so we can cover a wider application range. Second of all, make a lithography that combines photolithography and electron beam lithography in the same process, in the same wafer at the same level. So we can have like the quality of the EVL and the quantity of the photolithography. We want to develop a MEM-based tuner process so we can get reduced consumption and footprint. And in the third year, we hopefully will be incorporating sources and detectors through transfer printing. Each of the following slides, it is how we are planning to address each of these objectives. I'm running out of time, but basically they have what I have said. So I'm going to skip them. We're going to do this collaboratively with CNM, VLC, and also the MEMS clean room that we have in the Technical University of Valencia. And hopefully, we are here today covering this wavelength range. And in 1 year time, I hope that we are already covering this. In 2 years' time with modulator, and in 3 year times with sources and detectors. So that's it. Let me end raising the attention about forthcoming European conference on integrated optics that we are organizing in Valencia at the end of May next year. So please set the date. Call for paper is going to be issued at the end of the week, and the deadline will be by January. So please submit your paper, come to Valencia. It's a very enjoyable conference, technical conference, and also exhibit. Thank you. That is all.
Thank you for the very nice and complete talk. Just a short question. When you're looking for a device to be working after long design, details to optimize, to be used in telecommunication systems, you're looking mainly for 2 main features. It is the device to be working with 2 polarization as possible, with as less refrigerancy as possible, and to maximize the coupling between fibers and the device. Which platform do you recommend for this?
But what is your device, passive or active? That is the first question, maybe. Is your device is only passive or active?
Originally passive, but logically you later want to have some kind like switches or some kind of modulators inside.
Well, that's a tricky question. I would say that at least for yeah, that's a tricky question. It has not a single answer, but at least, I mean, if you want the polarization independence, straightforwardly, you should go to the thick silicon of VTT, for instance. That is a straightforward PTL-free, I would say. Or you can just resort to some silicon nitride. You play with the thickness and with the wavelength, and the cross-section dimensions to make them PTL-free. If you want to have modulators on it, well, that's tricky, because if you do that in silicon, you need implants, and I think there is no one around doing that.
Okay. Thank you.
Any other question? Yeah, we had a few questions during the presentation, so I think we can thank Pascual for his talk.
Thank you. Thank you.
And, now invite our next speaker, who Luis Orbe, and he's actually a former PhD student from UC3M. So we gratefully welcome him back to Madrid, and he's currently working as, well, you were working as application engineer, but now you